Good morning, everyone. Thank you for joining this morning on today's webinar, which is the OCS-I Digital I/O modules. It's slightly shorter than the past couple. It's roughly about 12, 13 minutes, but we'll get straight into it. And if you have any questions, we can get to them at the end.
Hello and welcome to today's webinar. Today we're going to be looking at the OCS-I Digital I/O module. Let's look at our agenda for today. We'll start by reviewing the Digital I/O lineup, what modules are available, and then we'll look at positive logic versus negative logic, syncing versus sourcing, and PNP versus NPN. We'll finish with a module by module breakdown when it comes to specifications and wiring, and there will be lots of application hints throughout. Let's get started. On the screen we have the lineup for the OCS-I Digital I/O modules. One of the most popular modules from a Digital I/O standpoint is the DIQ616 that has 8 DC inputs and 8 DC outputs. It's popular because in any system that has a significant number of I/O, that's the module with the highest density. And then we have some relay modules available. A mixed module with 4 digital inputs plus 4 relay outputs, and then a relay only module with a bit more current capacity. We also have an 8-point AC input module, and then also the 2 inputs and 2 outputs that are available from a Digital I/O standpoint in the CNX116 base. So that's the lineup today for the Digital I/O modules for OCS-I. Now we'll look at positive logic and negative logic. Positive logic, which is sometimes referred to as active high, is logic where a high voltage signal indicates an on condition or a 1, and negative logic, which is sometimes referred to as active low, is logic where a low voltage condition indicates off or a 0. And now we look at positive and negative logic as it relates to inputs. So on the right hand side at the top, we see a diagram for a positive logic PLC input. So we have a 24 volt supply there shown with the plus lead running through the switch. And then when the switch is asserted, that plus signal is on the input terminals. So when the input terminal is on, it has 24 volts there. So that is positive logic because when we have high voltage, we have a 1 or an on condition. Directly below that, we see the traditional negative logic connection, where instead of running the positive terminal through the switch, we run the negative terminal through this switch. And when the switch is thrown, we have 0 volts for an on condition. And then in the bottom left hand side, we see another approach for negative logic wiring, where the input module itself provides the signal which is run through the switch into the input terminal, which again is low voltage when on. Positive logic is the most common style of input, especially in the US and Europe, although negative logic inputs are still popular in Asia. Now we look at positive negative logic as it refers to output signals from an OCS. Now, it doesn't change the definition of what positive logic and negative logic are. So for a positive logic output, when the output is on, you have a 24 volt signal on the output terminal, which is then run to the load. And then with a negative logic output, when that output is on, you have a low voltage signal running to the load, and then separately, you have the positive voltage connected to the load outside of the output module. It is sometimes said that logic outputs are somewhat unsafe because if the negative wire connecting the output module to the load were to fall off, then potentially the load would turn on because of the external connection of the plus voltage to the load. So that's one of the reasons why negative logic outputs aren't used too often anymore. Another term you'll hear quite often is syncing and sourcing. We'll start with syncing and sourcing inputs. In general, a syncing circuit is a circuit where current is flowing into a device, and a sourcing circuit is a circuit where current is flowing out of a device. At the top right here, we have wiring for a syncing input, and we can see the current is flowing into the terminal for syncing input. And then at the bottom, we have a sourcing input, where current is flowing out of the input. And you can see that based on the wiring diagrams from our previous slides, syncing inputs correlate to positive logic, and sourcing inputs correlate to negative logic. When we look at outputs, again, the definition of a syncing circuit and a sourcing circuit does not change. But when we take a look at the diagrams, we can see that for a sourcing output, we have current flowing out, and for a syncing output, we have current flowing in. So in this case, a sourcing output correlates to positive logic, and a syncing output correlates to negative logic. So that's the relationship between syncing and sourcing, and positive logic and negative logic. Now we'll talk about PNP and NPN. These usually, from an automation standpoint, refer to sensor output. So it's what the output looks like on a sensor, whether it's PNP, NPN, or something else. A PNP sensor will have an output that produces a positive signal, whereas an NPN sensor will have an output that produces a negative signal. So when you look at compatibility between a PNP or NPN sensor and a PLC input, you'll see that they require different types of inputs. So for a PNP sensor, it needs to be wired to a positive logic or syncing PLC input, whereas an NPN sensor needs to be wired to a negative logic or a sourcing type PLC input. So that's where PNP and NPN come into play when you're trying to match your sensor output types and your PLC input types. Now we look at the different modules that are available for OCS-I-O. Firstly, the DIQ616. This has 8 DC inputs and 8 DC outputs, and that density, which is currently the highest density we sell, helps make it a very popular module. Some of the advantages are the fact that you can use either 12 volt or 24 volt signal levels with this module, and you can choose to use either positive or negative logic. On the output side, there are 8 solid half amp outputs at 24 volt DC, only available in positive logic. The outputs are short circuit protected, and there are 2 groups of 4 as opposed to just 1 group of 8. From a specification standpoint, one of the things that stand out on the input side of things is the fact that this is a 24 volt solid state input. It has fast response with 1 millisecond switching time and a typical 10 kHz input impedance. Next, we'll look at wiring on the input side. For positive logic wiring or syncing inputs, you just connect the plus lead from the 24 volt supply, run it through the input switches and into the input terminals, and then the minus side of the supply wires to the 0 volt terminal. For negative logic, you take advantage of the 0 volt terminal and connect that and run that through the input switches into the input terminal. So that is negative logic or sourcing input wiring. There are some extra 0 volt terminals available on the module which are just there for your convenience. From an output specification standpoint, the thing that stands out the most is the switching time, which is rapid at 1 millisecond. And there's short circuit protection with the output drivers as well. And then in terms of output wiring, it's positive logic organised into 2 groups of 4. And you can see what the wiring looks like here. There are 2 different voltage inputs to run the 2 different groups of outputs. So the V1 input connects to the DC voltage that routes through to outputs 1 through 4, and the V2 input connects the DC voltage that routes through outputs 5 to 8. Now we look at another mixed module. This is the DIQ512, which is a total of 8 I/O points, 4 inputs and 4 outputs. On the input side, it's basically the same specification that we just saw with the DIQ616. On the output side, instead of solid-state DC outputs, we have 4 relay outputs with a nice rating of 3 amps per point. All the output relays are isolated, which means they're not common together. However, if you want to common them together yourself, we provide extra terminals to make that easy, so that can be done in the field. As we take a look at the specifications, we see there's nothing different about the inputs from a specification standpoint as compared to DIQ616. And the wiring also looks similar, but we can only see the positive logic wiring there on the screen. It does also support negative logic, also wired in the same way as the DIQ616 inputs. As we look at the outputs, we can see some differences because we're talking about relays. So again, there are 3 amps rating per relay. Also the fact that there are 500 volts of isolation between the contacts and the ground on the module. And the relay types are type 1A, and the expected mechanical life of those relays is approximately 100,000 cycles. In terms of wiring, we can see here we have isolated outputs, which means each relay is wired separately from each of the others. Also, we can see fuses in the wiring diagram. Anytime you're using larger relay loads, you should look at fusing, and the rating for the fuses are going to be dependent on the load sizes and the wiring gauge. The next module we're looking at is a relay output only module. This has 4 relays and does not have any digital inputs. What makes this module different is the fact that it has more solid relays. So there's a higher current capacity per relay and a higher current total capacity for the entire module. Also, something to note is that because of the extra current running through this module, it only has a 50C max rating. So that is a small difference between this module and all the rest of the modules in the line. The only real differences in specification are the higher current values on the relays. They're still the same expected life and the same isolation to ground. And it's also the same wiring diagram, although the loads can be a little bit larger. Now we look at the AC input module that's available, the DIM620. The highlight of the DIM620 is the fact that it can be used with retrofit applications which require AC type inputs. So the maximum voltage is 120 volts AC. There's 1 group of 8 inputs, there's easy common distribution because there's all sorts of common terminals available on the terminal plugs, and one thing to remember is that all the inputs must be on the same phase. From a specification standpoint, one thing we notice is the fact that the AC inputs are obviously not as fast switching wise as the DC inputs. DC inputs would switch in about a millisecond, whereas with AC type inputs the on to off response and vice versa is closer to 20 milliseconds. For wiring, it's very straightforward. You just take the hot side of the signal coming out of the sensor, wire that through the switches and into the input terminals, and the neutral side gets wired to the common terminal on the module. Finally, we have the built-in I/O that's available in the CNX base. There are 2 flexible inputs and 2 DC outputs. The advantages of flexible inputs when it comes to digital I/O is the fact that not only do they support 12 volts and 24 volt levels, but they also support 5 volt levels. So if there are any TTL level type sensors or signals that you would like to connect to your system, the CNX base has 2 flexible inputs that are 5 volt compatible. Also, the output current capacity isn't half an amp, it's 2 amps per point. So that's a nice bonus when it comes to extra current capacity with the CNX 116. In terms of specification, the inputs are very similar when it comes to digital I/O, except for the fact that you can support those extra voltage levels, the 5 volt level and even a custom level. For output specification, the only thing that stands out is the higher current capacity. There's still the short circuit protection that's available on the other modules with solid state outputs. From a wiring standpoint, you can see the wiring for inputs is shown on the left and the wiring for outputs is shown on the right, and there's really nothing different there. Now we'll look at the plugs that are used with the digital I/O modules. They're all either 6-pin or 4-pin and they're all removable. They're spring clamp style, which means if you utilise ferrules, then you don't need a tool to insert your wiring, you just need a tool to remove the wire. Also, every terminal point is labelled, which makes it very easy to make sure you get the right wire in the right terminal location. We use 2 different styles of plugs. They're both removable, one is a 6-pin and one is a 4-pin. In terms of rating, they're nearly identical. The only real difference is the voltage rating. In addition to a small screwdriver you might need for removing wires, you're also going to want a medium-sized screwdriver for ejecting the plugs. Now we look at some of the final tips and tricks when it comes to digital I/O wiring. To make things easier, don't use a wire that's larger than it needs to be. For I/O wiring in most systems, 1 metric MM2 wire will have plenty of current capacity and will be easy to work with. We can see in the lower right hand corner the NEC National Electrical Code Machine Tool wire rating chart for the different gauge wires from 6 down to 1. And you can see that even 1 MM2 has 6 amps of capacity. Also, if you use ferrules, it is recommended that they come with the slightly longer 10mm barrel. If you use those, it'll be much easier to not only get the wires in the right place, but also to remove them if you need to. So that concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, so next week we do have our final video on the OCS-I in the last run we've had, and that is on configuring it. We can then see we can follow up with UDFBs again and then controlling a smart motor with can open. So all the registration links are there, and if you want to go back and watch this video or any past videos, you can just scroll down to the bottom of the webinar page and they're all available there. Okay, other than that, thank you all for joining us this morning, and we hope to see you again next week. Have a good day.